Hi, everyone. Welcome to Stream Processing Meetup. My name is Efe. I manage LinkedIn Kafka team, and my co-host today is Gary. He's a senior engineering manager in the Stream Processing group. Today, we have three amazing talks. First, we will start with a small introduction and FAQs. Then our first talk each talk is 35 minutes. Our first talk is from Confluent. It will be on Apache Kafka and HADR, a primer. The second talk is from LinkedIn. It will be about declarative data pipelines deep dive. And the third talk is also from LinkedIn, and it will be on optimizing Samza state management with Ambry Blobs, a deep dive into enhanced efficiency and C2S. So before we begin, I would like to share a number of frequently asked questions and their answers. Are the talks being recorded? Yes, we are recording the talks. And after the meetup, we post them to our YouTube channel, LinkedIn Engineering channel. The meetup event site will also have the link to the recording once it is available. How can I ask questions to the presenters? You can post your questions at any time during any presentation using the Q&A tool on Zoom. This is the button that is at the low bar at the Zoom window. And at the end of each talk, presenters will answer the questions in the order of popularity. And depending on the time, we may cover remaining questions after all talks conclude. If you would like to present in our meetup, whom should you talk to? There are a couple of options. You can either post a message on the meetup site expressing your interest. You can send a LinkedIn message to me or to Gary, or you can email again to me or Gary about that, and we can discuss. And without further ado, I'll stop sharing, and I want to introduce our first speaker today. Our first speaker is Danica. She's a staff developer advocate at Confluent, where she helps others get the most out of their event-driven pipelines. And prior to this role, she served as a software engineer on a streaming infrastructure team at Blobs, where she predominantly worked on Kafka Streams and Kafka Connect-based projects. Her expertise in streaming systems has taken her to a number of conferences and speaking engagements over the years, giving her the chance to express her love of Kafka to anyone who will listen. Danica is committed to increasing diversity in the technical community and actively serves as a mentor to a number of women in tech. With that, I will leave it to Danica.
Thank you. Let me figure out, hopefully we got the sharing down. All right. Hello, everyone. My name, yes, is Danica. I do look a little different from my photo that was on the meetup on the advertisement, but I promise I'm still Danica. I still work for Confluent. I'm still a developer advocate, and I will still talk ad nauseum about Kafka. And tonight we're going to talk about Kafka, although I'm very excited to be here for the rest of the talks. It's got a great lineup tonight. So thank you all for having me and for being here. So today we're going to talk about Apache Kafka and HADR. So who is this talk for? Well, anybody who is maybe building applications with Kafka, right? If you're an end user and you're building just applications, you're not really thinking about operating Kafka. You can treat it as that beautiful little black box that just serves up your data when you need it. But sometimes you're not so lucky, and it might be worthwhile to check into how that data is served up to you and what your options are to make sure that you can still get your data when you need it and what your strategies can be to make that happen. Or maybe you're just looking to vet Kafka for an application and you want to make sure that it can serve its purpose and do exactly what you need it to do, and you can configure it to make that work. So again, Kafka and HADR, very, very important. But I do want to let you know that I have a problem with acronyms. I hate them. I think they're incredibly alienating. So the first thing I'm going to do tonight is just make sure that we know what terms we're dealing with. And so the first one, HA, high availability, right? And so this defines an architectural strategy that seeks to create potentially redundant components of your infrastructure. And the purpose of this is to minimize or even eliminate the downtime of various areas of your system, right? So the bottom line is that basically we want our data and our applications to be available as consistently as possible, right? Sounds like a good thing. DR, this is disaster recovery. So in the event that a potentially debilitating disaster scenario occurs, and that sounds pretty intense, but this can be anything. This could be, a cloud outage, right? It could be something as goofy as, hey, we let the interns into the data center and someone trips and suddenly we don't have service, right? So a DR strategy is going to outline the steps that are going to be taken to restore service and ensure that whatever disruption to your regular business operations, whatever that is, that it's minimized. So again, HA, high availability, DR, disaster recovery, these both sound like really good things that we would want, right? So why don't we chase after them? So you might be building streaming applications. Why wouldn't you be? It's really cool. It's all the rage these days, computing things in real time and building your event-driven systems on top of these technologies. But in the context of Kafka, HIDR is really important, right? We're building these mission-critical streaming systems, and we want to make sure that they can work consistently, and that if something bad happens, that we can minimize, that bad thing, the effect of that bad thing, okay? So before we get into, we're going to be diving into a lot of what HA and DR individually mean for Kafka. But a lot of it is just built into the technology itself, right? You don't have to do too much to get the benefits of these things. So Kafka can very easily be accommodated as part of generally an architecture that's seeking a high availability and a disaster recovery solution. Okay. But to really understand how it does that, we need to be better acquainted with a little bit of the internal workings of Kafka. And specifically, these internal workings are what make Kafka really, really great for high availability. So I probably don't have to remind everyone about this, especially if you're already using Kafka, but I want to go back to some of the basics, right? How we actually store data in Kafka. So that primary unit of storage in Kafka is just a topic, right? And this is just a data set where we're storing events. You get data in using producers. Cool. We get data out using consumers. Awesome. A really important thing as you're building consuming applications on Kafka is that your consumers are able to keep track of where they left off. Right. And that's going to be a really important thing when we come back to high availability and disaster recovery solutions, because when something bad happens, we want to make sure that any consuming applications can pick back up where they left off. Right. So those offsets are going to come back. So these Kafka topics are not the only unit of storage in Kafka. They're broken down into smaller components called partitions. And these partitions are really important because they're they are the immutable append-only logs where the actual data are stored, right? And Kafka is a distributed system, so these partitions are going to live on different nodes across the cluster. And by doing that, we're going to provide better resilience of that data and facilitate the replication of that data for high availability. So again, to acquaint everyone with some of these, the basics. So the nodes of a Kafka cluster, these are going to be called brokers. And these brokers, they can be running wherever you want, bare metal, in the cloud, containers, VMs, pretty much wherever you need them to run. So this is a really simple setup here. Simple cluster, we have 3 nodes, 3 topics with some number of partitions, right? And your results may vary, but your partitions might be distributed like this. This is a pretty toy example, but in a real life scenario with more brokers, with more topics, more partitions, the overall goal is that we'd obviously want our partitions to be spread as evenly across these brokers as possible so that, just to reduce the load and spread that across all of the brokers pretty evenly. And that also means that we're kind of reducing the impact of any sort of broker downtime, because what happens if one of these machines goes down? So say we lose broker 0. Well, okay, that's unfortunate, right? Because we've taken at least one partition from each of these topics with us. So immediately, the producers that were writing data to those partitions and the consumers that were reading from those partitions, they're immediately impacted. They can't continue doing what they were doing, right? The good news, there is a silver lining, right? You may not see it at first, but the good news here is that only 1/3 of our data was lost, right? That's better than all of the data being lost. So by spreading this data across these brokers, across the cluster, we're already kind of mitigating the worst of the situation, right? But we're going to take it a step further with a built-in process called replication. So again, replication, it's built into Kafka. It's a configurable parameter that just determines how many copies of a given partition are going to exist across a Kafka cluster. So in this case, I've moved on to a different example here. We still have our 3 brokers, but instead we're going to look at this from the perspective of a single topic with just 3 partitions. So in this case, you'll see that our main partitions, the partitions that we're actually working with, we're going to call those leaders. Okay. And so we have partition 0 on broker 0, 1 on broker 1, and 2 on broker 2. And so what happens is that when our producer actually writes data to these partitions, we're going to write to wherever that lead partition is. But then we also have some backup copies. We have some replicas that exist across the cluster on other brokers. Okay, and this is because we have a replication factor of 3 enabled. This is the default, pretty standard. But when replication is enabled, once we've written the data to that lead partition, we're also going to replicate that data over to our follower partitions that exist on other brokers in the cluster. Okay, and so just as in the other example you saw, these partitions are going to be distributed evenly across the cluster, right? And specifically, we have 1 leader partition existing on each broker. Pretty convenient that we had 3 brokers and 3 partitions. It's not always as nice as that, but in this case, it worked out. And then again, we have those 2 additional copies of each partition spread across that cluster. And an important thing to note here is that the follower replicas of each partition, we really don't want them to live on the same broker as the leader, right? This is by design, because again, if a backup copy exists on the same node as the main one, then we don't get any benefits from actually having that copy, right? Because again, if a broker goes down for some reason, right, we lose that first broker. Well, okay, that's unfortunate. Again, we lost a leader partition and we lost some copies, right? 2 replicas. The replicas aren't as important, right? They were just backups. We can recover from that. But we lost that lead partition for partition 0. And that's unfortunate, right? Because immediately the producer that was writing data to that, the consumer that was reading from that, all right, they can't function anymore. But as soon as this happens, right, the cluster is going to realize that there's no leader for partition 0. And we're going to undergo a leader election process that's going to promote one of the follower replicas to be the new leader. So in this case, broker 2 will promote its broker 1, will promote its copy of partition 0 to be the new leader. And once this happens, whatever producers were writing to that partition, whatever consumers that were reading from it, can continue doing what they were doing with that new lead partition. All right. So like I said, Kafka already has this replication and this leader election process built into it. It's enabled by default. Just got to be a little bit aware of it. Please don't turn it off if you don't know what you're doing. But as you can imagine, when it's set up properly, when you know what it can be used for, this is great for maintaining a highly available cluster. And in some cases with this, again, this black box, you don't really have to think about this. Kafka is going to continue to serve up your data for you pretty conveniently. So just out of the box, Kafka is pretty highly available, right? We're going to use multiple brokers. We're going to distribute data across them, across multiple partitions for a topic. And then we can actually configure it to pretty much be a synchronous replication process for our data across these brokers. But that's just within a single Kafka cluster. We can ensure high availability. But okay, what happens if that cluster is, what if all the machines in that cluster are operating the same data center and it floods, right? Disaster strikes. Then suddenly, the high availability that we had doesn't really mean anything in this context, right? And that's where disaster recovery, where DR comes in, okay? And the best way to get around that is to spread your Kafka cluster across multiple geographic locations. So whatever durability and high availability that we just talked about, that's going to get even better in this situation. And then there are a number of disaster recovery options that are available at your disposal at that point. The biggest way to set up a disaster recovery, have a plan for your Kafka cluster is to use geo-replication, right? We're going to set up our cluster, across or within different geographic locations. And by doing so, we're actually going to provide some of the best RPO and RTO numbers that you can get. Again, acronyms, I really dislike them. So let's break it down. RPO, recovery point objective. So Recovery point objective effectively defines the frequency of your data backups, right? If you're going to set up some sort of disaster recovery plan, you want to be able to have a backup of your data, okay? So in the event that your system goes down, RPO tells you how much data do you expect to be lost when the system fails over to a backup system. RTO, this is recovery time objective. And again, as we're doing these sort of backups and we're failing over in a DR situation, RTO is going to define how much time you can expect to pass between the point where the system left off before the disaster scenario and the point where the system picks back up again, where it's failed over and we've resumed normal operations. So in the event of any sort of disaster scenario, you'd ideally have an exact copy of all the data that your business needs, right? If your data is being continuously replicated, which would be, again, an ideal situation, then your RPO, your recovery point objective, is going to be low, ideally 0. You're not going to lose any information when you switch over. And your RTO, your recovery time objective, would simply be the amount of time that it takes to fail over, to flip the switch and go over to that replicated data store that you can start operating off of again. So that sounds pretty good, right? Wouldn't we kind of want to reduce those two things? So how do we do that with Kafka? Well, from the perspective of Kafka, like I said, geo-replication is a big part of having a solid DR strategy, right? But to do that, you have to set up Kafka clusters either within or across different geographic regions. Pretty standard, pretty straightforward. But depending on your business use case, your requirements, there are a couple options that you have available to you. There are some trade-offs, and some of them are more complicated to set up than others. So let's jump into some of these strategies a little bit more. So the first one is to set up a single stretched cluster across multiple regions. It's exactly what it sounds like, right? We're going to set up a cluster, one cluster, but our nodes are going to exist across different geographic regions, maybe across different cloud availability zones, but we're still going to use a single Kafka cluster. By doing that, we're going to be able to take advantage of that, more or less that synchronous replication process that we can enable that happens by default in the cluster. We're going to get better durability, and we also get that automatic failover that we saw in that example where the broker went down, right? We're going to be able to immediately take advantage of the replicas that we have in that cluster. We're just going to have nodes that exist elsewhere, not in the same data center. So because of this, you get a lot of benefits, right? Your offsets are going to be preserved. That is the biggest thing you're probably concerned about when you have any sort of failover situation with Kafka, is that how are your consuming applications reacting, right? How do you know where you're picking back up, if you're picking back up where you left off, or if you're a little bit behind, right? Or if you've lost some data. So the ideal is that we want our consumers to pick back up exactly where they left off. So we want those offsets, those consumer offsets, to be preserved. We want our consumers to be able to immediately consume and from the follower replicas whenever any sort of failover occurs. That would be cool. That would be great. There are some limitations to setting up a stretched cluster. So in order for a stretched cluster to be successful, we can't really have the data centers be that far apart from one another, right? So that can be limiting. We're already stretching across cloud availability zones, maybe across countries. So depending on where your data centers or where the cloud availability zone is, we still need to be able to maintain a stable, low latency. We'll need a high bandwidth connection depending on what our latency needs are, right? And so that said, if you are using Confluent Kafka, if you're using any sort of Confluent clusters, we do provide the notion of observer nodes that help to loosen this requirement. And when you're setting up a Kafka cluster and you want that replication of data to happen across brokers, that can be configured, like I said, to be more or less synchronous. All right. But to lessen that burden, observers in multi-region clusters are going to asynchronously replicate that data from the leader brokers. But by doing so, they're not actually burdening themselves with as much effort as you would if they were balancing other needs of the cluster as well. So the observer nodes are able to asynchronously replicate that data and allow your data to eventually be replicated, again, without burdening your cluster with any sort of high latency synchronous replication. There's also, as you're setting up a stretch cluster, just more overhead involved, as you need to be careful about where your replicas reside. If you're using older versions of Kafka, you really had to be careful about where your replicas live, because obviously you'd want your replicas to live in the other data center, the other cloud availability zone, right? Newer versions of Kafka, they are rack aware. You can configure your brokers to be rack aware, so you can make sure, and that's already going to be built in, and your data is going to be balanced appropriately. But again, if you're using an older version, if you don't ensure that, then your stretch cluster isn't really going to give you anything good, right? You could potentially be in the situation that you were in before. So if you don't necessarily want to deal with the overhead of a stretch cluster, you might want to look into a multi-cluster setup. That might be more appealing. So in a multi-cluster setup, we are going to set up fully standalone clusters in different geographic regions or availability zones. And then we're going to have a separate third process actually conduct the replication of the data from one cluster to another. How you do this can vary. There's a couple different ways to actually make this happen. But before we get into that, I think it's useful to understand a few more use cases and strategies for replication in multi-cluster setups, because not every setup is the same. Not every it's not a one-size-fits-all sort of situation. So there might be some different options for you. So the first one is active-passive. So as the name implies, in this case, we're going to have one active cluster and one passive cluster. Cool, pretty simple. The active cluster is going to be the one where the data is actively being written to and consumed from. And then you're going to have a passive cluster. And the only data that's going through the passive cluster is the data that's being replicated to it. So the idea here is that the passive cluster is really just a hot backup of sorts, right? If our active cluster goes down for any reason, then we know that our data has been replicated over to our passive cluster. We can fail over our consumers and our producers to point to that passive cluster. And our consumers, in theory, should be able to pick back up where they left off. And again, this is most commonly used for backup scenarios where you only need that passive cluster for disaster situations. The next is an active-active setup. So in this case, we have two clusters that we are actively writing data to, and we are actively consuming data from, right? And then we're going to have a two-way replication process that is writing data between each of the clusters. The setup is really useful when you have geographic regions where data is being actively written to and consumed from, but maybe you want that information to be eventually available to all of your clusters globally, right? Think, maybe we have clusters in EMEA, we have clusters in APAC, but we want that data to actually be available to everyone eventually. The reason that you might want to be writing to those clusters more locally, again, to reduce latency and just serve up information more quickly to local clients. The next option would be a fan-in setup. So here we have potentially smaller Kafka clusters that are going to exist across a number of geographic regions. And then we're going to have any number of replication processes copy that data over to some centralized aggregate cluster. And we're going to do that maybe for longer term storage, for other sort of data consumption, longer term analysis. This is a good option if you want local applications and clients to be able to connect to and write to regional clusters for lower latency, and then do more intense analysis later on from the larger aggregate cluster, or just have that data, again, stored in a longer term in a different area. And then finally, we have a fan out scenario, which is effectively the opposite of fan in. So here we'd have some large centralized cluster where data is actively being written to regularly. And then we have many processes selecting maybe all or maybe just some subset of the data for replication to smaller regional clusters. And again, so that could be for the purposes of local clients getting the benefit of faster pulls from the smaller clusters. Okay. So those are a couple options that you might have or reasons why you might want to set up clusters across different geographic regions. But now let's get back to the main point at hand, is like, how do we actually do this replication process, right? And so the biggest way to do this is to use something called Kafka Connect. At the most basic level, Kafka Connect is a way to move data into and out of Kafka. So these connectors, typically just defined ways to connect to data sources, to data sinks where data resides at rest, or we might want to move it to out of Kafka. So think databases, pulling data from the other end of an API, moving it into Kafka. But in this case, we're going to use Kafka Connect to bridge the gap between the two clusters for the purposes of replicating the data. So usually you set up a source connector to read data and move it into Kafka, or a sync connector to read data from Kafka and move it out. But we're going to have a connector that does both. I lovingly like to call them SOINC connectors, but that is not an official approved term. Please don't repeat it. But I think it's fun in my head. So depending on your Kafka distribution, if you're using open source vanilla Kafka or Confluent Kafka, you can either use Mirror Maker for vanilla Kafka or Replicator for Confluent clusters. And you can use either of these to replicate that data between your clusters. So again, consumers and their offsets, really important. It's going to keep coming up because that's critical in these situations. The really important thing when we are moving data between clusters is that we need a way to translate these offsets, because when you are writing data to a destination cluster, the offsets are going to be different, right? We may have cleaned up some data on the source cluster, and maybe the offsets are, pretty large, and then we write to the destination cluster that might be small, right? So we don't have a direct, the offsets aren't going to be the same. So in either case, with Mirror Maker or Replicator, we need a way to translate these offsets so that when we flip the switch, when we fail over to our destination cluster, that our consumers know what offsets they're actually working with, what they're using. All right, so Mirror Maker and Replicator, these are great options for multi-cluster setups. They're available for both vanilla and Confluent Kafka, and they're pretty flexible in how they're set up. But I think the only downside of these is that you do have to maintain a separate kind of Kafka Connect cluster to run this replication process, which introduces some overhead. If you are happy to run Kafka Connect, and which most people are, and that's completely fine, then yeah, this is a great option for you. For those of you who are using Confluent for your clusters, we have Confluent cluster linking available to you. So this is a built-in Confluent capability that mirrors your data, right? Replicates your data to a destination cluster, but it does more than that. It also replicates topic configurations, the structure, and mirrors the consumer offsets. So that's really critical as well, right? So unlike Mirror Maker and Replicator, this is built into the Confluent brokers. There's no additional infrastructure, no Kafka Connect cluster that you have to maintain or any connectors. And you can easily and quickly start replicating your data seamlessly between these clusters. Other cool features of it that I think are pretty cool are this is byte for byte replication of your source topics on your source cluster to what we call mirror topics on the destination cluster. So these mirror topics are going to maintain exact offsets. So again, in that situation where you're failing over, our consumers are able to seamlessly transition during a failover to this other cluster. And building on that byte for byte replication, these mirror topics and the destination cluster are completely read-only to ensure the integrity of your source data as it's being replicated. We can also migrate and replicate full access control lists so that you can customize your deployments. And again, make sure that when you fail over your destination cluster, everything is set up the way that you need it to be. It can be used as part of a hybrid setup, right? Where you're mirroring an on-prem cluster, either a Confluent cluster or even an open source Kafka cluster to Confluent Cloud. And another cool thing is that it's flexible in setting up include and exclude topic lists. You can also add prefixed topic names to your mirror topics as well. So manage which applications data is being copied from your source cluster to your destination cluster. And the whole thing is set up pretty easily over a REST API or a CLI command. So it's pretty convenient to set up. All right. We covered a lot of different options. It's meant to be, again, sort of a primer just to show you what's available and what Kafka is also under the hood doing for you to make sure that your data is available to you when you need it. I included a link to my link tree here. I have a couple of resources there. Specifically, there's a really cool article on multi-region Kafka cluster setups, outlining some of this information, but going a little bit deeper into those setups for you. And I have some additional links to our Confluent developer portal, which if you want to go deeper on Kafka, or if you want to back up and just get a good introduction to the technology, we have a lot of courses available on that portal. So with that, I think I have some time for questions, and I will happily go through those.
All right. Awesome. Thanks, Danica.
Yeah.
Let me read the questions ordered by the upvotes. The first question is from Akash. So Akash is asking, how do you set up such observer Kafka broker nodes? Seems like you'll need to ensure the broker is not a preferred replica for any partition it hosts. But even then, there is a chance some partition's leadership comes to this broker if another broker dies in the stretched cluster.
Sorry, I need to read this again. How do you set up? Yeah, so in that case, the observer nodes are specifically set up so that situation does not occur. I can send you, actually, I can get your name and I can send you a couple of resources on Confluent Developer and some of our docs that actually outline this setup. But again, this is specifically for Confluent setups. And so if you hit any sort of difficulties with this, then your account executive, your solutions engineer can make sure that you're setting this up properly. So again, we are specifically configuring this not to be the case, so that situation is not actually hit.
So next question is from Mahesh, I believe Mahesh RK. With active cluster, can consumer still read from brokers by preserving order?
Okay, so you're saying in the situation in the active cluster, if we're writing to the same topics on each cluster, that's what I'm imagining your situation is. So if we are writing to the same sort of topics for the same types of applications on each of our active clusters, when we replicate that data over, there could be overlaps, inconsistent data. In that case, your order is not preserved. So you kind of have to, you want to avoid cyclic replication in that case. So it's not like we're going to take application A from the destination cluster application A's data from cluster A and replicate it to cluster B, and also take applications A data from cluster B and replicate it to cluster A. We, in that case, would set up prefixes on those topics, or that's what I would do if I had to get into that situation, and have some other process be able to resolve that ordering. But no, out of the box, you are going to have some issues, and you're not going to be able to guarantee the preservation of ordering.
Right. So next question is also from Mahesh. Would the single stretch cluster increase the latency with X equals O? Also, would the observer guarantee the 100% data replication if the leader goes down, since it is async? Okay.
Two-part question. Yeah. So in the single stretch cluster, absolutely. If you have X, all your latency is going to go up. It is how it is. That's another reason why you might not want to go for that option. But I've seen this work successfully in many situations. The key point here being that we really need our data centers to be as close as possible. I'm talking I've seen situations where we needed to have low latency and the data center was in New York and we had one across the river in New Jersey. Like, that was almost too far away, right? So that's something you definitely need to take into consideration if you want to maintain that low latency. With the observer, guarantee 100% data replication if the leader goes down, since it is async. So you could have some issues on that. The nice thing on the observers is that we are not burdening the rest of the cluster while this happens. Their sole purpose is to just make sure that data is replicated over, and they're focusing only on that. The same situation can effectively happen even in, a normal cluster with axe-all. That process can be configured to be mostly synchronous. But even with axe-all, we're still waiting for other brokers to request that data is replicated. So in my experience, it's no worse than what you're going to get, for the replication in a regular cluster.
Thank you. So next question is from Saravanan. How quickly the leader election happens? Could you share some latency numbers on different scenarios?
Off the top of my head, no, but I can send you some resources on that. So how quickly does the leader election process happen? Within a couple hundred milliseconds at worst, depending on when the metadata is refreshed on that cluster as well. So it's relatively quick. Those things can also be, if you need to have that happen more quickly, those are configurable.
Right. So those were all the questions, Danica. Thank you very much for answering them. With that, I will pass it to Gary to introduce our next speaker.
Great, thank you. And if you have any other questions, feel free to reach out to me. And if I promise you resources, I will go back and track you down. So thank you, everybody.
Thank you. All right, I'm Gary Yang. I'm a engineering manager in LinkedIn for stream processing team. So allow me to introduce the second talk of the evening, titled Declarative Data Pipeline Deep Dive by Ryan Dolan. So Ryan works on data pipeline infra at LinkedIn. He's the primary author of Hoptimeter and Mirror Maker, and he lives in San Antonio, Texas, and has 6 pinchers. All right, take it away, Ryan.
Cool, thank you. Yeah, the pinchers are dogs, in case anyone's wondering. Yeah. All right, cool. Let's dive in. So yeah, declarative data pipelines. Sorry, my camera's kind of blowing out on me, but all right. Let's see if I can progress slides. There we go. All right, so data pipelines. So at LinkedIn, we have a lot of moving parts that engineers sort of piecemeal put together to implement data pipelines to move data from point to point. These systems sort of collectively I would call the data plane. These include systems for processing, transferring, transforming, caching, materializing, that sort of stuff. And so a lot of these systems, of course, probably in the present audience would be familiar, things like Flink, Samza, also Goblin, Brooklyn, and even to some extent you can consider like something like Pinot or Venice, which is storing derived data as part of like the data plane. So those are the sort of systems that I'll be talking about. Cool. All right, so if you are building a data pipeline out of these systems, this usually comes up, or this often comes up, when you have data in some database, something like Espresso. Espresso is one of our internal databases, and you want to move data from, say, Espresso into Pinot, Apache Pinot, an open source, another type of database. And you might find yourself wanting to do this because, for example, Espresso has different performance characteristics, different capabilities than Pinot, right? So if you have data in one type of database and you want to get into another type of database, you end up building a data pipeline to move data from point A to point B. So you might use Brooklyn to capture change events. So Brooklyn at LinkedIn is used for CDC, change data capture, basically tailing updates from a database like Espresso. We might use Beam to do some stream processing, maybe transfer those change events into a Kafka topic so that we can ingest that data into Pinot. So this sort of thing comes up quite frequently, right? But actually, it's not quite this simple. If you sort of zoom in on Brooklyn, you'll see that Brooklyn actually has 2 hops internal to the CDC part of this pipeline. So data actually goes from Espresso to a Brooklyn connector. Database level changes land on one Kafka cluster, and then those database level changes get picked up by a second Brooklyn connector, which lands table level changes into a second Kafka cluster. And then these end up, this is essentially what gets processed by, say, a beam job, right? So even when you're just saying, from a high level, I want to get data from Espresso into Pinot, which seems like a simple thing, you very likely are to encounter multiple hops. So this like multi-hop data pipeline thing is sort of what I've been looking at for the last year or so. And of course, even if you're just going from A to B, that's not that interesting, right? Usually you have to do some sort of business processing, business logic, and you may need to like look up data from some other location, like another Kafka topic, and maybe you're materializing data into Venice and that sort of thing. So this is a pretty common scenario where you're lost my mouse. Sorry. Where your data is coming from multiple sources and you have to do some sort of like join inside of a beam job and that sort of thing. Cool. All right. So title of the talk is Declarative Data Pipelines, right? So at LinkedIn already, we have a sort of declarative API that abstracts over the CDC part of a pipeline like this. So we have something called the data stream API that the Brooklyn team owns. And so the Brooklyn data stream API lets customers that are maybe making a beam job, for example, instead of trying to talk directly to, say, Espresso, they can just talk to the data stream API, and the data stream API gives them back a data stream, which is a change stream from some source of truth like Espresso. And the nice thing about this is, all those hops in between that I mentioned, those are all sort of automatically created. So a user just needs to create a data stream, and all the complexity underneath there is automatically taken care of by Brooklyn. So customers tend to really like this. They don't have to worry about, am I talking to Espresso? Am I talking to MySQL? Am I talking to, database XYZ? They just need a Brooklyn client, and they can consume from any sort of data stream in roughly the same way. So that's what we're talking about when we say like a declarative API. We can just create a data stream and then start consuming from it. So we're looking at this like, we like this model, and we're wondering if we can extend this model to not just encompass the CDC part of data pipelines, but the entire data pipeline, right? Wouldn't it be great if we could have a declarative data pipeline or declarative API for creating data pipelines that include things like Kafka topics, Venice, even maybe the Pinot table, right? So that's sort of like the gist of this talk. What would it look like if we were able to abstract the whole data pipeline just in a declarative behind a declarative API? So as this slide sort of hinted at, one way to do this, one way to sort of like express the pipeline is SQL, right? And if you start thinking about data pipelines in terms of SQL, you quickly realize that data pipelines are basically just materialized views, right? So data pipelines are, they're sort of the same concept, the same thing, they're just used in different contexts, right? So in data pipelines, we tend to think of them as like producer driven, in the sense that we're empowering someone to produce data and get it somewhere, right? So if I'm a data pipeline engineer, I'm responsible for constructing these pipelines that deliver data somewhere. Whereas with materialized views, it's more consumer driven, in the sense that someone asks for data, right? They say, create me a view, and I don't care how it got there. This is just the data I need, right? But under the hood, it's sort of doing the same thing. If you're looking at data pipelines or materialized views within like a SQL context, you might have like an insert into to create a data pipeline, and you might have like a create view to create a materialized view. But they're, again, roughly the same thing, just sort of expressed differently. Data pipelines tend to be disaggregated, distributed, piecemeal, ad hoc. That big, multi-node graph that I showed in the previous slide. That's the sort of stuff that data pipeline engineers end up using, right? They're using Kafka, they're using Beam, they're using connectors to move data from multiple sources to multiple sinks. That's sort of the data pipeline game, right? Whereas materialized views, they tend to be sort of internal and automatic, but they're usually limited to a specific type of database, right? So for example, we have Espresso materialized views at LinkedIn, but you can't use Espresso materialized views to materialize data anywhere but Espresso, right? That's pretty typical scenario. But the point is they look very similar, right? And they're sort of doing the same thing. And if you look real closely, you'll see that in the SQL context, both data pipelines and materialized views are really just queries, right? They sort of like are made up of a query, right? You see like the select star from or sort of thing inside of a data pipeline or inside of a materialized view. So we want to like sort of drill in on this fact, right? If data pipelines and materialized views are the same thing, and they're really just queries, this yields sort of an interesting way to think about data pipelines. So it begs some questions. Can we make data pipelines as easy as SQL views, right? Data pipelines tend to be complicated, a lot of moving parts. SQL views are all automatic and internal to a database. Sort of the inverse of that question is, can we make SQL views as flexible as data pipelines, right? Like what if we could just say create view and get data from wherever it happens to be, right? That would be pretty great. So when we start thinking about along these lines of defining data pipelines from SQL, so we can think about data pipelines just as streaming queries that continuously update a materialized view, right? So out of that sort of analogy, I'll throw some terms around here that are all essentially the same thing. So when I say pipelines, I'm really just meaning like streaming queries. And when I say streaming queries, that doesn't really it doesn't work that well in the context of data pipelines. Like, I don't know, queries seems to me like, request response, which is not what pipelines are doing, right? So I don't like to use the term queries in this context, but that's sort of what they are at a fundamental level. So to sort of like, smooth over both these terms, I use subscriptions. So you'll hear me use subscriptions throughout the rest of the talk, but a subscription is just a streaming query that is implemented by a data pipeline, right? Right. So the goal here is how do we go about creating this streaming data pipeline as subscription thing, right? So we kind of have like this concept in mind. How do we go about building it? So Apache Calcite will help here. Apache Calcite is a database framework, among other things. So if you've heard of Apache Calcite, you've probably heard of it as a SQL parser or a query planner or optimizer. And so right there, that should hint to you that maybe we can use it as a pipeline planner, right? If queries and pipelines and subscriptions are all kind of the same thing, materialized views, all kind of same thing, why can't we use Apache Calcite to plan our pipelines, right? And that's sort of what this talk is about. It's, we were able to do this to some extent. Also, we'll need some place for our pipelines to run. So LinkedIn started using Apache Flink fairly recently. Apache Flink is a framework for stream and batch processing. And it's nice because it supports SQL, and streaming SQL and batch SQL. So we have like, if we can describe a pipeline in SQL, Apache Flink seems like it might fit within this story. So let's talk a little bit about Flink real quick. So Flink sort of has a runtime, like at the very bottom of this complex stack we'll talk about. And the Flink runtime lets you create tasks, and I just use ops on my slide. They call them operators, but in the context of this talk, that's really confusing. So ops, operations, operators. So on top of the Flink runtime layer, we have the Flink table API. This introduces tables and connectors. And on top of that, we have Flink SQL. So here's where Apache Calcite comes in. So Flink SQL is essentially Apache Calcite used to assemble pipelines out of tables and connectors in the Flink table API. So Flink plus Apache Calcite has this, has already been, gives us Flink SQL sort of already. So with Flink SQL, which, exists today, it's an open source thing. You can write a little bit of SQL and you get a Flink job that will consume from data sources, do some transformations, write to data sinks, that sort of thing. All right, so if you kind of look inside what the Flink job is doing, you'll see that there are a bunch of connectors that connect to external data sources, data sinks. And then there's a bunch of ops, again, like these operations, things like joins, projections, filters, that sort of thing, that make up the Flink job. So turns out Apache calcite's really only used to plan the ops inside of that Flink job, right? So Apache calcite's the smart query planner thing that understands SQL, but it's really sort of only used to plan like these operations that happen inside of a Flink job. Which sort of begs the question: who is creating these connectors? Who's configuring these creators? Or who's configuring these connectors? Who's talking to the external databases? Who's setting up these external databases and that sort of thing? And unfortunately, the fact is with Flink SQL today, that's basically you, right? You're the one configuring the connectors and creating syncs and stuff like that. So with Flink, with Apache Flink, going back to our sort of like complex, landscape of data pipelines things, Flink fits really well in sort of like the middle here, the stream processing piece of this puzzle. So Flink SQL works really well here. And we talked about the Brooklyn data stream API, which fits really well for the change data capture aspect of this pipeline. But unfortunately, there's still a lot of moving parts that you have to sort of manually create, right? And in fact, you sort of have to manually create the Flink SQL. So this helps, but we haven't quite solved the whole problem. So the state of the art for declarative data pipelines at LinkedIn today sort of looks like this. We sort of have Brooklyn data streams, which covers the change capture use case, CDC use case, again, grabbing updates from a database and presenting them as a stream of changes. Brooklyn is also used for change capture views, which is basically like lightweight transformations of a CDC stream. And then we have Flink SQL, which is great for lightweight stream processing, lightweight batch processing. But these are two different systems, and they don't have much in common other than that they're both sort of declarative. So I mentioned this concept of subscriptions, right? So the idea that we started investigating over a year ago now is, can we sort of like merge all of these things together into one high-level concept, which we just call subscriptions? And subscriptions are basically streaming SQL queries, as I said, and these sort of subsume the concept of change capture streams, change capture views, stream processing, batch processing, all into one big high-level construct. All right, so this sounds pretty good. Now that we have this like subscription concept, we sort of need a subscription API. Ideally, right, we should be able to like create a subscription, give an API some SQL, and then the pipeline should go be created magically, right? So that's sort of the idea here behind a subscription API. Well, it turns out we have done this to some extent at LinkedIn. This is extremely experimental, early. This is not like any sort of recommendation, or this is more like just like a proof of concept that we've been working on, right? So this project is called Proteus, and Proteus is basically a subscription API, which is like CRUD operations on subscriptions. So you can create, delete, update, that sort of thing. Underneath the subscription API, it's powered by this open source project called Optimator, which we created earlier this year. And Optimator is basically the control plane. It's a Kubernetes-based control plane for data pipelines. And Optimator leverages the Flink Kubernetes operator, Brooklyn operators, and other such Kubernetes operators. And all this runs on Kubernetes, right? So this is what basically the rest of the talk is going to be talking about. So, and then specifically, I'm going to talk about Optimator because it's the open source component here. Again, early days, very experimental, but it's out there. You can take a look at it. So Optimator is basically this control plane for data pipelines. It sort of owns and creates all these things, taking the place of human engineers before that had to create and piece all these different moving parts together. Okay, so Optimator is kind of cool. It has an interesting concept, which I'll try to explain. the core concept behind Optimator is tables with baggage, okay, which probably is a terrible term, but bear with me. So tables are not a new concept, certainly. Tables have been around for as long as data has been around, right? And the Flink Table API and Flink SQL and many other such frameworks understand tables or represent data in terms of tables. So what Optimator does is sort of extend that table model, and instead of just presenting data as a table, or as using tables as like an interface to data, in Optimator, the tables sort of take ownership and have control over all of the moving parts behind that data. So for example, a Brooklyn data stream, which is powered by multiple Brooklyn connectors, multiple Kafka clusters, we can sort of bundle that all up as a table. So it's like the table with baggage is sort of the concept, and that'll hopefully make more sense as we go. So the idea behind baggage is that a table can bring along its own infra. So this infra is super open-ended. It can be really anything. Specifically, baggage can be SQL transformations. It can be DDL. For example, Avro schemas can be, or not Avro necessarily, but like SQL data types and stuff can be carried along as baggage with a table. As I mentioned, CDC streams, Brooklyn data streams, that sort of thing can be baggage. A table can have an intermediate Kafka topic, for example. It can have its own materialized views or caches. Sort of an interesting thing that we've been playing around with is that tables can carry around their own ACL rules, their own access control list rules, right? So, for example, a table might carry around the infra required to grant itself read access, right? Which is kind of cool. And sort of the most easy thing to understand is that a table can bundle its own connector configuration as baggage. So we'll see what this looks like. All right, so the Optimator project, like I said, it's open sourced, very, very early. None of it's been released or anything other than just thrown out there, right? But the Optimator project has two main components: the Optimator CLI, CLI, right, which is useful for issuing ad hoc queries. It's not for production, but it's great for debugging, and I'll show some screenshots. And then there's the Optimator operator, which is a Kubernetes operator, and it's responsible for deploying end-to-end multi-hop data pipelines based on user-provided subscriptions, right? All right, so well, we're going to talk about how Optimator can be extended. How can Optimator be useful to you? Well, Optimator can be extended with adapters. So this concept of adapter is borrowed from Apache Calcite, which Optimator is based on. And both Apache Calcite and Optimator have this adapter concept where it's essentially plugins, right? So the Optimator adapter API has sort of three layers to it, or three different components. We'll go through them each in turn: the catalog, the operator, and the planner. Okay, so first off, the catalog. So the catalog in Optimator is all about tables and databases. And I'll throw some code up at you. So at the core of Optimator's catalog is this concept of a hop table. A hop table is just a table with baggage, okay? So hop tables actually extend Apache Calcite's abstract table class, and therefore they have normal table stuff like a name and a row type, which is sort of like the table schema. So when you see row type or table schema, we're talking about the columns and the data types that are in the table. But in addition to this normal table stuff, hop table has this baggage concept, which are collections, or you see here script implementor. So script implementer is how you would carry around arbitrary DDL, arbitrary SQL, and the resources are how you carry around any other arbitrary things. So it's super flexible, and I'll show you how that works. In addition to hop tables, the Optimator catalog API has a concept of a database, of course, not surprising. Database is kind of interesting. It's made up of these functional interfaces. So a database has a table lister, which lists a bunch of table names. So this is responsible for identifying all the things in a table. A table resolver takes a table name and maps it to its schema or its row type, the columns and data types in the table. And then there's a table factory component that takes a table name and constructs a hop table from the previous slide, right? So you usually don't actually have to implement a hop table yourself. There's some factories that'll do it for you. One is the probably more common one is connector factory. So a connector factory takes a configuration and produces a hop table for you with all the DDL and SQL and stuff bundled up automatically for you. So if you have a connector, like a Flink connector, like for example, the Kafka connector for Flink, then you can just configure it and give it to the connector factory, and it will give you a hop table to access, or that uses that connector, basically. I know that's a mouthful. So to make it a little bit more concrete, here is the table factory interface. You can see we're just returning a hop table. And here's the connector factory constructor, which just takes configurations and returns a table factory for you. So usually this is all you have to do, and they'll show some examples. So a database is usually just a table lister, which very often is a one-liner, you'll see. A table resolver, which also is usually just a one-liner. A config provider, which is how you encode like the connector configuration, how to configure a connector for, say, something like a Flink connector. And then optionally, a resource provider, which provides these resources, which is that baggage concept. All right, so an adapter is essentially a database factory. Okay, easy enough. All right, here's an example. You'll probably have to squint, but I'll walk through it real quick. So this is the full implementation of the data gen adapter in the open source Optimator project. So we'll see in the code, you'll see that it's creating a hop table here. You see new hop table, and it's creating data gen person as a table, and it's creating data gen company as a table. And oh, by the way, data gen just means it's generating fake data for testing purposes, right? And then down here we have it returns a database with the two data gen tables there. So we have some random people, some random companies, and those are in a database. If we look a little closer, we'll see that the row types are defined in this hop table statically. So we're defining name, employee ID, and that sort of thing. Same down here. This is name and CEO. You'll see these are the row types for these two tables. And finally, you'll see some connector configs, and specifically these are Flink connector configs. So Flink has a data gen connector. So to use Flink's data gen connector from a Optimator adapter, we just need to provide the corresponding Flink connector configuration, and that's what this is. You're saying connector is data gen, number of rows 10, fields age min is 0, and so on. And same here. All right, so that's the sum total of the adapter for the data gen adapter. So now that we've implemented the data gen adapter, we can actually use it. So here's me firing up the Optimator CLI. So this lets me, like debug and poke around the catalog. So here I'm saying describe person, and you can see that this data gen person shows up in the catalog with the columns, name, age, employee ID, and the corresponding data types. Not too surprising. From here, I can actually query. The data gen adapter, right? Or the data gen database that's implemented with my data gen adapter. So I'll say select star from data gen person, and you'll see that I'll get results. Here's some random names, random ages, random employee IDs, which are unfortunately sometimes negative. I probably could fix that. And then you'll see up here that there's some logs generated. So Optimator CLI is using the adapter that we wrote on the couple slides back, right, to automatically generate some Flink DDL and Flink SQL to actually implement this query. So when I say select star from data gen person, it's actually like sort of unpacking all this baggage and then running the corresponding Flink job. So you'll see that my row type shows up here in the Flink DDL. You'll see that the Flink connector configs show up here in the DDL. And then this is what is actually run. So an interesting thing here is that the Flink, or sorry, the Optimator CLI is actually dynamically creating this Flink job and running it locally in order to get these results, right? And this whole thing takes under 4 seconds, which I guess is not too bad. All right, so let's look at a slightly more complicated adapter. This one is also in the open source project. There's not much to it. It's the MySQL CDC adapter, okay? So you'll see first off that we are talking to MySQL through the JDBC client. So then our table lister here, which is one of these functional interfaces, we just have to call jdbc.getTableNames, and that's the full implementation of the lister. That's it. Our table resolver, likewise, we just get a tables row type, and that's the full implementation of the table resolver. Here's our Flink configuration. We're using the MySQL CDC Flink connector. If you know a lot about CDC, you might be surprised to know that this actually is Debezium under the hood. So this adapter is using MySQL and Flink and Debezium to accomplish this CDC stuff, which I think is pretty cool. And then ultimately we're returning a database with our name, our lister, our resolver, our connector config provider, and that's pretty much it. That's the sum total of the MySQL CDC adapter. And now that we've written this, now we can tail MySQL and with subscriptions and get change data capture as if we had set up like a Kafka Connect cluster with Debezium and all that. Cool. So one more implementation I'll show. This is the raw Kafka adapter. So the raw Kafka adapter exposes Kafka topics with a static row type. You see that we just have payload and key. There's no schema registry or anything here. It's just the raw payload. Here's the Flink connector again. And then here's our implementation of a table lister, which in this case just takes the Kafka admin client and calls list topics. That's pretty much it. So it's not a one-liner in this case, but it's pretty close. Scrolling down, you'll see here's my table resolver. It's just returning our static row type. So literally, really, I mean, couldn't be easier. And then here's when things get kind of interesting. So we haven't seen this before, but here's a resource provider. And this resource provider is providing these resources, which again, I'm kind of calling baggage. So this is a Kafka topic that we're carrying along, and these are Kafka topic ACLs that we're carrying along. So this table basically can grant itself read access anytime you read with it, or write ACL anytime you write with it. That's sort of what's going on here. And then ultimately return our database, which is name, table lister, resolver, connector config, and this resource provider. That's it. So a little more complicated because there's these resources involved, but still, like, dozen or so lines of code. All right, so this resource concept is pretty fuzzy and hand-wavy at this point. What is a resource? A resource is essentially a YAML file, and this is because we're using Kubernetes. We're, Optimator is targeting Kubernetes, so YAML files tend to come up a lot, right? So in Optimator, there's this concept of a resource, which is just a bunch of attributes, and resource templates, which render a resource into YAML, essentially. So I can actually show this in action. The Optimator CLI has a YAML command, so I can issue a YAML command, this YAML command with a pipeline. So here's my pipeline. Insert into queuing, select star from tracking. Queuing and tracking are just two Kafka clusters. Okay. And this YAML command will spit out all of the YAML that the catalog will generate when I need to access these tables. So here I have a Kafka topic. You see like page view event shows up. You see Proteus test sync shows up. There's a bunch of other resources that are generated. Here's an ACL. This is a write ACL. This is a read ACL, and so on. All right. So the catalog API in a nutshell is hop tables and databases. It's table listers, table resolvers, and table factories. Usually you don't have to actually implement a table factory. You can use a connector factory for the same purpose. And ultimately, this is just configuring connector with a config provider. And then finally, we talk about resources, resource templates, and which are essentially YAML files. So that's the catalog API. All right, real quickly, we'll talk about the operator. So if you have a bunch of YAML files, you need those YAML files to actually do something. And that's where in Kubernetes land, that's where the operator concept comes into play. The operator is all about controllers and reconcilers. So the key takeaway here, and this is sort of like the whole point of Optimator. Like this, if you don't remember anything else from this like really fast-paced talk, it's that Optimator with adapters can leverage existing Kubernetes operators. That's sort of the takeaway message here, and I'll show you how. Okay, so you would imagine that since I've been talking about Optimator and Flink, and Kubernetes for that matter, a lot in this talk, you would think that Optimator would be like deeply coupled with Flink. You would think that Optimator would sort of depend a lot on Flink, but that's not the case. Optimator only leverages Flink using a Flink adapter. There's actually a module called Optimator Flink adapter, and this is the entirety of the Flink adapter. So I think this is pretty cool. Like the coupling between Optimator operator and the Flink operator is just this. So on your left, you see a resource template, and on the right, you see a controller provider. This is the plugin for the plugin mechanism for the operator, and the Flink controller provider just registers an API. It says, hey, you can create things called Flink deployments. And that's it. We don't even need anything else. Why? Because we're leveraging an open source existing Flink operator. So someone else has done the hard work for us. It's called the Flink Kubernetes operator. It already exists. All we need to do is tell Optimator how to create Flink jobs, which we do with this template. And then that's it. That's the end of the story, which is, I think, is pretty powerful. So you can kind of imagine, right? Like if you wanted to target other things besides Flink, other runtimes, other systems, say Beam, and there was an off-the-shelf Beam operator, you know, there's ways forward here, sort of low-hanging fruit for extending Optimator to do more interesting things than just run Flink jobs. All right. So if there is a
Ryan, just do a quick time check here.
Well, how much I got? I have no idea.
Minutes right here.
How many? Was 1 minute?
2 more minutes.
Oh, cool. I got like 2 more slides. Awesome.
Perfect.
Thank you. Secondly, adapters can implement their own logic. So I'll just buzz through this real quick. But there's a Kafka controller plugin. This is part of the Kafka adapter, which implements a Kafka topic reconciler. This is just taking care of creating Kafka topics and stuff. This is not a talk on Kubernetes, so I won't talk about how to do this. But if you've created an operator before, you can actually just drop it into an adapter, which is kind of cool. Finally, the planner is also extensible. You can drop in your own rules and converters. And here's just, so the idea here is that adapters can manipulate the planner, which is Apache Calcite. Here, so you do this with rule providers. This gets really complicated, so I'm not going to spend any time on it. And also, I don't have any time. But you can see you can drop in custom rules, and these do things like this one. This is turn SQL into a Flink job, basically. This rule provider is what the CLI uses, the Optimator CLI uses to run Flink jobs locally. And that's pretty much it. I'll show you what this looks like real quickly when you're actually playing with Optimator. Here's the CLI. Let's see. I already showed you. This is the plan. This is the SQL it's generating, heavily redacted, so there's not much to look at. This is the more SQL that it's generating, blah, blah, blah. Here's the YAML. I already showed this, that it's generating. I also have a mermaid command, which is really cool. I added this not too long ago. The mermaid command will spit out diagrams. So here's some example diagrams. This is using the DataGen adapter. This is using the Kafka adapter. This is using the Brooklyn data stream adapter. This is using the Brooklyn data stream adapter with a join. And then that's basically what I've got. You can basically see that you can create subscriptions, and then you see the corresponding SQL, and you get all of these things as a result, like Kafka topics get created, Flink jobs get created, and so on and so on. That's it. So I guess I lied. I had like 4 more slides.
All right, thank you. Thank you,
Thanks.
Ryan. Pretty cool stuff. If you need questions, reach out to Ryan and check out this Optimator open source project. In the interest of time, I will introduce our last talk of the evening. The title is Optimize Samza's State Management with Ambry Blobs, a deep dive into enhanced efficiency and cost to serve. We have 2 speakers for this talk. Anchor is a staff engineer who works on LinkedIn's Blobs store, also named Ambry. He began his career in Intel research building binary translation systems for detecting zero-day attacks. Some of his work was adopted by McAfee antivirus when it was part of Intel security. He has worked on distributed data and storage at a startup and also at Oracle Cloud before joining LinkedIn. Along with Ambry, he contributed to Apache Gossip and Gem 5. The other speaker is Shekhar. Shekhar is a senior engineer working on the managed stream processing team. He has worked extensively on Samza engine, focusing on state management, and has contributed to several improvements in this area in open source Samza. Prior to LinkedIn, Shekhar worked at Salesforce on Activity Metrics, a platform that powers the real-time metrics at Sales Cloud. All right, take it away, Ankur and Shekhar.
Thanks, Gary. Shekhar, do you mind sharing the slides? Sorry.
Thank you, Gary.
I guess I see the speaker view. Perfect. Thank you. All right, so let's get started. Welcome to this third and final talk of today's Streams Meetup. Already night. My name is Ankur. I'm joined with my colleague Shekhar. I won't go into the introductions. Thanks, Gary, for doing that. So today we are going to talk about optimizing Samza's state management with Ambry Blobs. So let's get started and look at the agenda. Next slide, please. Here's the agenda for this talk. We'll start with a quick overview of Samza and Ambry architectures. We'll then describe a state management problem in Samza. We will talk about the integrated solution that involved both Samza and Ambry. As you would expect, a project of this scope has a number of design, architectural, implementation, operational challenges. Towards the end, we will quickly touch on a few of the interesting ones. If you have to take away one thing from this presentation outside the technical concepts that we'll cover, it will be how one of the teams at LinkedIn had a real business and performance problem, and how the solution for that came not just with very close collaboration between the teams, but also continued improvements in both the teams, which are the 2 large distributed system product at LinkedIn. All right, so at this point, I'll hand it over to Shekhar to talk about Samza's architecture.
Thank you, Ankur. So I'll start with a brief overview of what Samza is and how we use it in LinkedIn. Samza is a large-scale distributed stream processing engine. It's highly scalable, fault-tolerant. It provides a durable local state and fast recovery from failure. At LinkedIn, we run Samza jobs beneath the Beam API layer. Beam is the portability layer on top of Samza that supports multiple languages, and it provides a unified interface for both stream and batch processing use cases. At LinkedIn, we have a massive production deployment of various Samza jobs. We process more than 4 trillion events every day. We have more than 3,000 jobs running in production on more than 15,000 physical hosts in the fleet. At a very high level, some important concepts in Samza. So Samza, the streaming side of Samza depends on Kafka. The execution side depends on Yarn. And on top of that, there is a processing layer provided by Samza API. Samza has a concept of task, which is the logical breakup of the larger task you're trying to perform, and it provides the basic unit of parallelism. Then there are containers, which are the physical units that actually execute these tasks. you can consider this as a GVM that has one or more tasks running inside of it. Then there are coordinators. The task that coordinators performs is that they assign these tasks to different containers. They keep a check on the liveness of the containers. And if a container dies, it moves around these tasks so that they can continue processing as they were doing before. At LinkedIn, we have multiple different use cases for Beam and Samza, this entire platform. For example, real-time machine learning feature platform. So this enables our real-time AI and provides fresh features and embeddings. It's the standard platform over which we run both streaming and batch jobs using the similar and same logic, actually. It's the tracking platform that powers the product monitoring and analytics, and it's used across our platform to detect and prevent abuse. Let's move to Ambry architecture, and Ankur will talk about that.
Thanks, Shekhar. Let's move on to the next slide. Ambry is LinkedIn's blob store. It's a distributed storage system that is designed to be highly available, horizontally scalable, and very, very reliable. It was created at LinkedIn and open source in 2016. Do check out our GitHub repo to learn more. Next slide, please. Before that, I want to note that Ambry at its core is a handle store as opposed to a key value store. While Ambry does provide a lightweight key value layer, most of the applications use Ambry as a handle store for the consistency and reliability guarantee it provides. And we'll look at some of them later. So here are some of the numbers to qualify some of the characteristics I just talked about, to basically qualify some of the adjectives that I talked about. We have more than 5 nines of availability. The P95 latency to download small blobs is less than 50 milliseconds. And our clusters, we have multiple of them. Our clusters are of petabyte scale. Next slide, please. As you can see, Ambry is a feature-packed storage system. But in the interest of time, I want to highlight 2 key features real quick that make Ambry unique. Next slide, thank you. Ambry stores multiple copies of its data in geo-replicated replicas. Any of these replicas can accept concurrent blob uploads. So it's a multi-leader system or active-active system. Given a multi-leader system, Ambry is unique in providing strong read after write guarantee. That means if a blob is uploaded in one of the data centers and is followed by a get from a remote data center immediately after the upload, the get is always guaranteed to succeed irrespective of any replication lag. Next slide, please. Here's a very high-level view of Ambry's architecture. 3 main components are data node, front-end node, and the cluster manager. Data nodes provide persistence layer and store Ambry's data. Ambry randomly groups data into virtual units called partitions. Each partition has multiple replicas for redundancy and availability. A disk on a data node can contain multiple replicas of different partitions. The front ends receive HTTP requests from clients, perform some processing like access checks, encryption, decryption, compression. They also determine the partition to which the request needs to be routed and route the request to the data nodes containing the replicas of these partitions. The cluster manager keeps track of the state and health of the cluster and location of various replicas of each partition. Next slide, please. Thank you. Again, it's a highly available storage system with a lot of moving pieces, but for the context of this talk, I'm going to talk about 3 key architectural points that is going to be very relevant as we move on. Next slide, please. Let's get into them one by one. Ambry uses quorum-based consistency model to guarantee high availability and performance with strong persistence guarantees. The quorum policy is configurable. As an example, as shown in the diagram, on a put request, Ambry sends data to the 3 replicas of a partition in parallel. A separate configuration defines a success target, which is the number of replicas that should return success to the front end for the front end to return success to the client. A similar flow happens for delete. This quorum provides us with a good balance between persistence guarantees, good availability, and good performance. And obviously, all the aspects of this quorum is configurable. Next slide, please. The next key detail that I want to talk about is the asynchronous replication. In the last slide, we saw how we use quorum to synchronously write data to multiple, but a subset of all the replicas of a partition. Other replicas learn about this data via asynchronous replication. This replication tracks the ordered log of each replica. A typical replication topology is shown in the figure. Within the local data center, the replicas use all-to-all replication, while a designated leader replica, which is shown here in blue, does cross-colo data, the cross-data center or cross-colo data replication. One key point to note here, which will become relevant a little later, is that while asynchronous replication is fast, our lag is of the order of few minutes in the worst case. Within local data center, it's actually few milliseconds. However, there is always this replication lag, whether few milliseconds or a minute. Next slide, please. And the third and the final key architectural detail that I want to highlight is the background compaction. As I noted, Ambry stores data in partitions. A partition in Ambry is implemented as an append-only log file in a pre-allocated large file. Blobs are sequentially written to multiple partitions as put entries. The delete entries and TTL update entries, like the delete and TTL updates, get their own entries in the log file, making them soft update operations. So in order to actually clean up the deleted or expired data, Ambry uses a background compaction process that copies out all the valid data, and as shown in the bottom half of the diagram, might shrink multiple log segments into a single log segment. We will look into how these architectural details are important for this talk. But before that, I'll hand it over to Shikhar to talk about state management.
Thank you, Ankur. So I'll briefly introduce how Samza manages state, what the problems were, and how we solved it. So what are stateful jobs? Stateful jobs are those where tasks can store and query local data through APIs that Samza provides. So Samza local states allows a job to read and write large amount of data with a good performance. All this state that we're talking about is local to a task. If you remember from earlier, task is the small subunit of larger task that a job is performing. So there is no connection over the network. The performance is really good. This is akin to your SQL query where you would write a join or a group by. Any such query where there might be an intermediate state, think of a Samza stateful job like that. Some common use cases are window aggregation. So let's say if you wanted to count number of page views for every user every hour, or say you wanted to do a stream join. So join a stream of ad clicks with ad impression stream, or if you wanted to do table stream join and so on. Let's talk about the current state of state management with Kafka. So currently, like I said earlier, each task has a local state. The state within the task is managed by an in-memory database called RocksDB. Jobs can read and write these key value pairs to RocksDB database. And RocksDB here is responsible for persisting that state onto disk when and how it requires. So periodically, we will flush that state on the local disk. And that state is the RocksDB state. How we do it, periodically we run something called a commit, and it's configurable. Tasks have access to their own partition of this large data store. So each task is running a small data store, and it has access only to its small partition. So they don't interfere with each other. The state that we constantly write for each RocksDB store is replicated on a fault-tolerant Kafka changelog stream. This Kafka changelog stream is also log compacted, which will be important in our later discussion. So what that means is, if a task is writing same key value pair multiple times, eventually what you'll see in your Kafka changelog topic is the last key and value. So all of this together allows us to move a task independent of other tasks in anywhere in the cluster, and it doesn't affect any other task but itself. So what are the current challenges and why we needed to move away from this solution? Number one and the biggest is our bootstrap time. So what is a bootstrap time? It's the time it takes from the moment we started the job to the time until the very last container, and every single container has started processing input stream. That's called a restart or a bootstrap time. Some jobs that had very large states, even some partitions that may have very large state, it takes a very long time to actually bootstrap the job or the individual partition or task. We tried different solutions to fix that. The easiest was host affinity. What that means is when we are restarting a container or a task, we try to always restart it on the same host so that we can reuse all that state that we have been writing locally on the disk. That solves the problem, but not always, because a host can go out of rotation because of disk corruption or other maintenance activities. Also, Yarn sometimes is not able to place containers as effectively. Then we implemented something called restore parallelism, where a container that has multiple tasks, they can all restore from different changelog partitions in parallel. We also use something called a bulk load mode. This is a special mode of RocksDB that is very optimized for reads, for writes than read. So what that means is when we are restoring, we're trying to optimize it for write as much as we can so that we can reduce that restore time. Again, this solves the problem, but not completely. And then we have something called hot standby container. These are replica containers that are running in the background that are actively copying the state of an active container. And if that active container, for whatever reason, goes down, these hot standbys can immediately pick up. They can become the new active, and they can continue processing. This solves the problem of that long bootstrap time, but not really completely, because now we have two containers doing the same task. And as you can imagine, the cost to serve is now double than what it was before. There are other challenges too. For example, consistency guarantee for the local state. So if you remember, those changelog topics are log compacted. So the local state that you're seeing today, where you're writing a key value repeatedly, overwriting a value for a key, well, the final value that you see in the changelog topic is the final value that you wrote for that key. So it's eventually consistent. We can't guarantee that consistency. What we can do is we can use the minimum compaction lag for the changelog topic. That should reduce the frequency of that compaction. But now we are increasing the size of the changelog topic, and then it doesn't really solve our bootstrap time. So we are doing a trade-off of one problem with the other. There are certain limitations on Kafka topic itself. For example, there is an upper limit on message size. And there is a limit on the total store size a task can create. Why? Because it is correlated to the maximum partition size on Kafka. Can we solve it? Not really, not completely. We have tried to increase the message size, but we can't indefinitely solve it. We can only delay it. So what is the new solution? All that problem that we discussed so far, a lot of them are related to the changelog topic and how we are using it to backup and restore state. So we decided to move away from that completely and use a different solution. In this case, a blob store. And in our case, Ambry is the blob store that we use internally. So I'll talk about how this solves our problem while also explaining what our implementation looks like. So this is how it looks like now. At every commit, and if you remember, commit is when we persist everything. At every commit, we do a synchronous call to RocksDB and ask it to do something called a checkpoint. What it does is RocksDB can create a very cheap and in time fast checkpoint for the state that it has right now at that moment. How it does it? Well, it creates a checkpoint directory, and all the local state that it has on disk, it just creates a hard link of that in this new checkpoint directory. This means there is no physical copy of the files, just a link, just a Linux hard link. So it's very fast, very cheap. Once that's done, the job can go back to processing. The task can go back to processing. It's not blocked anymore, and it's very fast, so we don't block for very long. Once that's done, next what we do is we mark this new checkpoint directory with a unique checkpoint ID. We will see later how it's useful. This checkpoint ID is written as a file in the checkpoint directory, and it uniquely identifies this new checkpoint directory. Now, unlike the changelog topic that we were using before, Ambry has no limitation on how we write blobs or files to it. Also, just to remind you, Ambry is a blob store, which has no concept of a directory or a file. It just knows blobs and blob IDs. So what we do now is, in parallel and in bulk, we upload the entire content of checkpoint directory to Ambry. which in turn returns us unique blob IDs for each file that we uploaded. So this way we solve the problem of slow uploads or slow checkpointing for each task. All the tasks independently are uploading in parallel. That's very fast. But as you remember, Ambry has no concept of directory. So how do we create that concept of directory in Ambry? Because when we restore, we need that checkpoint directory structure as is, as RocksDB expects it in that moment. So what we do is we create an in-memory data structure we call snapshot index blob, and we'll talk about that later in the slides. But very briefly, index blob is just an in-memory map of the file metadata that we just uploaded to Ambry and the blob ID that Ambry returned for it. So metadata and blob ID is all that it is. Once everything is uploaded from checkpoint directory, we serialize this index blob that we have been building in memory, and we also upload that to Ambry. Ambry then returns as an index blob ID. Now this single blob ID is a pointer to all the checkpoint files that we uploaded to Ambry, and we can recreate this entire directory structure whenever we want to. It's a very cheap way of querying what's in Ambry for this specific snapshot. Once we have the index blob ID, we have another smaller in-memory data structure we call checkpoint. So the checkpoint ID that we created earlier, if you remember in step 2, that plus this last blob ID that we received, we serialize both of them and we write it to a Kafka topic we call checkpoint topic. This is a very cheap read, very cheap write. And whenever we want to read it, it's a very cheap read because it's a very small, tiny data structure that we are serializing and writing to Kafka now. So as you can see from the slide, what we did so far was upload everything in one go, but that's not very efficient because if we create RocksDB checkpoints in 2 instances of time, not everything within checkpoint directories change. So sometimes some files are deleted, few files are added, but a lot of files stays the same. So if we were uploading everything, we would be very inefficient in the way we are handling things. So go back to the index blob that we created in the previous structure. What we do is at new checkpoint uploads, we use the previous index blob that we created in memory, and we create a diff of the new checkpoint directory with the previous index blob that we created. What that gives us is a diff of what needs to be uploaded, what remains in Ambry, and what needs to be deleted from Ambry. That's a very efficient way of calculating the diff, and it's very fast. Let's look briefly at what this snapshot index is. I won't go over everything, but very briefly, a snapshot index looks like this. It has files present, which has file name, file metadata, meaning the size, the C time, the checksum, etc., and the blob ID that Ambry returned for it. So it's a list of all the files that were present in snapshot directory. If you see in the bottom, there is also something called subdirectories present. This is used to recreate that directory structure that was lost in Ambry when we uploaded blobs. There is something also called files removed and subdirectories removed. We will get to this later, but it keeps track of the blobs that we are going to delete from Ambry. It's very useful, and we'll see how later. So now you must imagine that in a system like this, containers can fail anytime, any moment. So what happens to all the blobs that we keep uploading? What happens if containers fail before we are able to reach the very final point of writing the checkpoint? Well, what we do is we upload all the blobs to Ambry with a very small TTL of the order of few days. So if our container fails before we can write a checkpoint to the checkpoint topic, which will finally complete the commit, if it fails, Ambry can automatically clean up these blobs after the TTL is expired. What happens if after the commit is complete? Well, after it's done, we issue something called a reset TTL to Ambry, which resets the TTL of all these blobs and tells it to never expire those blobs, so they can stay forever. And at any point if the container fails, container starts, and the first step a container always does is check the checkpoint topic, get the latest index blob, issue reset TTLs for all the blobs associated with this index blob, and also delete whatever needed to be deleted, assuming we might have failed in the previous step. All of this is idempotent, so if we did it multiple times, that's not a problem. So what was the effect of this new system? The effect and gains were pretty big for us. For example, we saw massive improvement in our bootstrap and restore time, which was one of the key objectives for us. So in this graph, I'm showing a job that's not even the largest job that we have. For this specific job, the bootstrap time used to be in the tune of 50 hours. So that is how much time every single container, the final container, will take to start processing input messages. We reduced that all the way to 45 minutes. Some other gains. In the past, if we had to do OS upgrades, it would be difficult because we would have to do it in the rolling basis. Well, we can't hit too many containers of the same job, or we might risk running into high lag for that job. So what now we can do is, with this new system, we can shift the traffic from a specific cluster, upgrade OS of all the machines, and then shift traffic back. The jobs can restore very fast from Ambry, and there is very little downtime in this entire thing. We were also able to reduce the cost to serve by a lot. So if you remember from previous slides, we used to have a hot standby container, which would double our cost to serve. Well, we can get rid of them now. And the savings we have from some of the large jobs we are running in LinkedIn is in the tune of multi-million dollars. So it's a big saving for us. As you can imagine, during the rollout and implementation, there were multiple operational challenges. So Ankur and I will talk about some of the top ones. I will talk about some operational challenges from Samza side. One unique problem we faced during this rollout was that of a corrupted snapshot. So as you remember, our execution is done via Yarn. Yarn actually manages the execution of all the containers and is responsible for its life cycle. So what happens sometimes is that Yarn is not able to cleanly kill a failed container. How it matters? Well, sometimes there are two containers for the same ID running parallelly. One that is supposed to not run, and one that is the actual real container that is supposed to run. So what happens is that this container that we call now the orphan container, it is in its course of commit, it doesn't know that it should stop, it should not process. It deletes some blobs, which is a regular operation during our commit cycle, right? So we do delta uploads, which includes uploads as well as deletes. And it's committing like nothing has happened. In that process, it can delete some blobs, which might corrupt the state that we have saved in Ambry. Well, the unclean shutdown of these containers can create a corrupt snapshot. And now our real container will also fail because it expects a certain blob to be in Ambry, which is gone now. So the way we fixed it was multi-pronged. The first step was to actually actively find and kill these orphan containers through various automated jobs and metrics. The second was in collaboration with the Ambry team, where now we have a certain duration of time where Ambry guarantees that delete is a soft delete. So if I delete a blob now, Ambry guarantees that it will still be in the data center for a fixed period of time, and it's configurable. They also provided us with a get deleted blob. So if we request a blob with this API, it will return the content of that deleted blob within that time period. Using that API endpoint, we can now download the content of the blob. What we do next is recreate the entire snapshot again in Ambry so that we don't have a corrupted state. And then we create a new checkpoint in the checkpoint topic. So now, if there were two containers, an orphan and a regular container running, they have diverged because they have different checkpoints and they don't interfere with each other, while our automated process will find the orphan container and kill it. Next, I will let Ankur talk about the operational challenges from Ambry side. Ankur?
Thank you, Shikhar. Thanks, Shikhar. As we already mentioned earlier in the talk, that this was an initiative where Ambry and Samza collaborated together, and we both worked in lockstep to improve, fix issues, and address issues in both our systems. This is a huge project. We had a number of challenges, and from Ambry side, I have picked top two, which were interesting. So let's look at them one by one. Next slide, please. The first one is write after write consistency. In order to get a flavor of what write after write consistency issue looks like in Ambry, let's consider this example. As we saw earlier, Ambry uses a quorum-based consistency model. In this example, on getting a request to upload a blob, the front end sends the request to 3 data nodes and waits for success from only 2 of the data nodes. In this case, data nodes 1 and 2 were able to successfully upload the blob, but data node 3 was down and couldn't take the upload. The request overall met its quorum, so the client got a success. Next slide, please. After this operation, this is the state of the data nodes. Note that other replicas will eventually get the blob via asynchronous replication. Next slide, please. However, asynchronous replication has a lag. Immediately after the write, only 2, and as shown in the diagram, immediately after the writes, only 2 of the data nodes have the blob. Next slide, please. Now assume a delete request arrives for the blob in this state. But before the delete request, the data node 2, which was one of the data nodes holding the blob, goes down. At this point, the delete request cannot succeed because the front end cannot get quorum for delete. Next slide, please. So this example is only one of the many flavors in which the write after write consistency issue can show up in Ambry. The general theme of these errors is that replicas holding the data can go down for multiple reasons, and replication of data to the data nodes not involved in quorum has a replication lag. So within the replication lag window, update operations might become unavailable. Next slide, please. We solved this problem in multiple phases. We started by allowing the update request to go cross-colo. This eliminated all the errors where replication got a chance to replicate the blob before the update request actually arrived. In the next approach, we limited the blast radius of error during replica failure by ensuring that repeated update operations are more fault tolerant. Ambry splits user blobs into chunks and create a special metadata blob that stores the chunk IDs. For repeated update or delete request, Ambry used the status of this metadata blob to determine if the operation had already been applied. And finally, as a more complete solution, Ambry implemented on-demand replication. This is very similar to read repair in a lot of databases. In on-demand replication, if the data is present in at least one Ambry replica and the request fails only because of lack of quorum, then Ambry replicates this data synchronously to other replica and then accepts the update. Next slide, please. All right, so the next interesting problem that I'm going to talk about today is compaction. Note that the way Samza uses Ambry, every minute, while Samza containers write multiple terabytes of data at checkpoints, they also invalidate the previous checkpoint. This can translate to multiple terabytes of delete per minute too, and deletes in Ambry are soft delete. So Ambry uses a background compaction process to clean up the deleted data. The problem with compaction is that if it is too aggressive, it competes with user operations for disk I/O. If it is too slow, a lot of deleted or expired data can accumulate on the disk and overwhelm the disk. Next slide, please. Thank you. As opposed to the previous problem of write after write consistency, the solution for compaction actually needed a lot of experimentation and fine-tuning on Ambry side. Full compaction scans that compact the entire log segment cannot keep up with the rate of deletes and will also end up using too much disk I/O. So we work to strike a balance between two knobs: how to limit the disk I/O for compaction and how to delete the maximum amount of unwanted data using the limited disk I/O. To limit the disk I/O, Ambry has the ability to throttle compaction if it crosses a configured disk I/O usage. To get maximum benefit from this limited configured disk I/O, we built stats-based compaction. Stat-based compaction aims to choose the minimal set of log segments that would provide maximum gains with limited I/O use. To get the right balance, we experimented with multiple values for compaction disk I/O, the relative cadence of stats-based compaction and full compaction, and the multiple methods to choose the best log segments for compaction. Note that we still need to run full compaction for GDPR and other purposes, but now full compaction needs to run less frequently. Using some of these experiments, we were able to find the right balance for compaction for various Ambry clusters. Next slide, please. So that pretty much finishes up the content of our presentation today. Last but not the least, I want to give a huge shout out to both the teams. A lot of interesting problems and solutions we just talked about came collectively from multiple individuals in the team. Next slide, please. From discovering the problem to creatively working on the unexpected challenges that showed up, every team member plays a crucial role in keeping both Ambry and Samza up and running. Next slide. That's all for today. Thanks for joining us, and I would open the floor for Q&A.
Thank you. Thank you for the talk. We may have time for one question. Katie asked, have we thought about using network file system as a solution to persist the state for Samza? If host affinity also works, then you can mount back to the same network file system.
Yeah, so I can take that. Yes, it could work, but then we are trying to also move to a system that provides us with replication and other good things for free. So moving to Ambry actually provides us with a lot of disaster recovery scenarios. And two, we do not want to manage another key piece in this entire puzzle. So we don't want to manage NFS, like a remote NFS system, and then replicate it and take care of its maintenance and so on. So moving to a solution like Ambry takes care of a lot of that problem for us.
Okay. Thank you. All right. With that, we'll wrap up the talks for this evening. If you have any questions, please let us know. If you want to have any kind of topic suggestions, reach out to Afe and myself. All right. Have a good evening. Bye.
Everyone, thank you.